Okay, so can you see my screen okay?
Yeah, we can.
All right, so it's always a great pleasure to come to Imperial. Very fond memories of my many different times there. And I'm going to tell you about more or less a program of research which has not yet constructed the path interval for gravity, but promises a new route to doing that. And so I'm quite excited about this. I think it will have lots and lots of applications, and it's extremely fundamental. I should say that, let me just begin by telling you how my perspective on fundamental physics has evolved. You know, I was part of the generation which made, you know, thousands and thousands of new models. And we had all sorts of fairy tale scenarios about the universe. And then at some point, and partly through being director of Perimeter Institute, where I was actually responsible, unlike most researchers, I was responsible for making choices and strategic choices. I had to really think carefully, you know, where is this field going? Because the honest truth is that it's not had any success in matching observations, you know, for a long time. And there is really no evidence for anything beyond physics, beyond standard model physics and gravity. And so I've come to the point of view that what we really have to do is have a new look at the foundations of the field. And that's actually very exciting. When you examine the foundations closely, you realize that things are far from solid, that people have proceeded on the basis of assumptions and hunches, and these were justified in all kinds of ways, but they're not firm. And the path integral is one of the least firm and most important. So all known physics can be summarized in this equation, which I've used in public lectures just to impress people, that in a certain sense, we have succeeded in describing nature with a very small number of fundamental laws. And I'd like to make the point that the founders of this formula, you know, we like to think of the lonely genius that all of these men represent, but actually on the experimental side, I think Marie Curie doesn't get enough credit because she really discovered the first experimental evidence that the laws of physics are probabilistic in nature in her pioneering works on radioactivity. And of course, Emmy Noether founded the idea that symmetry was fundamental. Symmetry and conservation laws were fundamental to physics, and that had huge influence throughout the 20th century. So, but here they are anyway, these basic laws of physics, and I'm particularly pleased that Higgs has two terms, though when I gave a talk in France, people complained that there was no French person there. So I've added Lagrange, who gets the V of the potential energy, which is also the dark energy. And here they are, and it's a very impressive achievement. Now, until recently, when I presented these talks, I would say, of course, we still don't know all the laws of physics because of the cosmic dark matter. There seems to be some kind of matter that isn't described by the standard model. But a couple of 3 years ago, Latham Boyle and I realized that's not necessarily true. That actually the standard model, including neutrino masses, contains the perfect candidate for the dark matter, which is the right-handed, one of the three right-handed neutrinos. And one can rather easily restrict the parameter space of the model and have one of those right-handed neutrinos be the dark matter. So that's a very interesting story, but that also helped me rethink, you know, what we're doing in fundamental physics, because I think typically people add stuff. They think that by adding more and more to the standard model, it will eventually simplify and everything will make more sense. But I take the opposite point of view. I think we should try and do more with less. We ought to understand these laws more deeply. And perhaps when we do, we will see that actually the solutions lie within these laws we already know. So in particular, the path integral. It's a very beautiful formula. We all learn it in graduate school. It's the most elegant and concise summary of quantum physics of continuous systems. And it sort of unifies everything. But there's one very basic problem. Do path integrals exist? Are they meaningful at all? And when you press your quantum field theory lecturers, they will tell you, well, of course, they don't really exist with the eye. You have to do a Wick rotation. And then you can start to prove things about existence. But really, that's a very violent thing to do. And I began to doubt that actually through working with Stephen Hawking, because he was convinced of that point of view. And I worked on it with him and quite quickly came to the realization it really doesn't work. Wick rotation doesn't work for gravity. And there are many other reasons, which I'll explain why it's not a good idea if you want to describe dynamics of quantum systems. So does this formula make sense? Now, it's a very difficult formula. It's at some level very elementary, because all you're saying is that the amplitude for any physical process is a sum of phases. We have e to the I theta, and we add up all the e to the I thetas, and that's the amplitude. And that's really the essence of quantum mechanics in many ways. And it's beautifully represented in this formula. But as I said, there's no idea whether this formula actually makes sense, if it converges, or if it's meaningful. Of course, you can use it for perturbation theory. And in fact, people make very strong arguments that perturbation theory, on the basis of perturbation theory and the S matrix, that we're forced to go to string theory and extra dimensions, et cetera, But that may all be another fairy tale, because this is possibly a non-perturbative formula which has all sorts of magic within it, if only we can understand it. So the essence of the path integral and quantum physics is interference. And of course, it's universal. And I'm going to give you, just to demonstrate that, some examples at the end of the talk, that you can calculate interference patterns in radio astronomy. And using these new techniques I will describe, we've solved some very old problems. People didn't know how to compute the interference pattern created by a binary gravitational system or any more complicated gravitational lens. But using path integrals, we were able to solve that problem recently. So interference happens on a cosmic scale. You just have to think of radio waves crossing the whole universe. They comprise photons. And if you keep track carefully of the phase, the quantum phase of those photons, that gives you everything you need to calculate the intensity pattern of the radio waves on your radio telescope. And these photons of radio waves have really traversed very largely separated paths right across the universe and maintain their quantum coherence throughout that journey. So interference happens right across the universe. Now, our real interest is in this theory, quantum geometrodynamics, which is really a pictorial theory invented by John Wheeler and others a long time ago. And the idea was very simple and compelling, which is that if you want to do quantum gravity, you need to consider how the different possible four geometries interfere with each other. So you set up an initial three geometry and a final three geometry, and then you sum over all possible interpolating four geometries. And there are some subtleties that come in there, like topology, different topologies, for example. But in principle, this is what you do. And you weight each four geometry with the factor with the phase I just showed you, e to the is over h bar, where s is Einstein-Hilbert action. And this should give the amplitude for any process in quantum gravity. So it's a very beautiful idea. And from my point of view, is surprisingly underexplored. And part of the reason was this Wick rotation, which really made it difficult. But if you read Wheeler's papers, it's very clear that he saw interference as key to understanding how classical space-time emerges. Now, there's a very fundamental paradox at which prevents us unifying quantum physics with gravity easily, which is that the whole idea of geometry, which underlies general relativity, is that locally a space-time should be flat, that it should be smooth, and the metric should be differentiable, and so on. But in quantum mechanics, as I'm sure you all know, the typical paths which contribute to the path integral, and this is this picture is from Feynman's book on path integrals. The typical paths are not differentiable. And this is actually forced upon you by the Heisenberg uncertainty principle, that somehow out of superposing these classical paths, you have to recover the fact that x and x dots do not commute. And the way you're able to do that is precisely because these paths are spiky and not differentiable. And this is all nicely explained in Feynman's book. So I think it's very likely, and it seems to me compelling, that the only way a smooth classical spacetime is going to emerge from a quantum theory of gravity is if all these wildly quantum spacetimes interfere destructively and this jaggedness smooths itself out. And in our studies, we're already seeing evidence of that, which is very interesting. Now, as I mentioned, the traditional approach to defining path integrals rigorously is line one. Take the propagator, let's say in ordinary quantum mechanics, from position x0 to position x1 in a time t. So take that expression, the path integral, the expression, formal expression or operator expression for the propagator, and replace the time t with minus I h bar beta. And then this becomes a matrix element of a Boltzmann-like operator. Positive, real probability. And so that's the traditional approach. It was introduced by Mark Katz long before Wick, because Katz happened to be at Cornell and he saw a talk by Feynman on path integrals. And he said, hey, I know how to make this meaningful. Let's make the time imaginary. But it's a very mathematical trick. Nevertheless, it's not very physical. It has absolutely dominated quantum field theory for 3/4 of a century. And I think it's time for that to stop. Because, why? Well, interference of phases and thermal equilibrium, thermal physics, are extremely different physically, and especially for gravity. And gravity is in general incompatible with thermal equilibrium. That's why the universe is not static, it's expanding. And so why are we using thermal physics to model quantum amplitudes? It's really a very deep and misguided direction. I'm not saying it can be the best you can do in many fields. For example, if you want to calculate the spectrum, the mass spectrum, then lattice gauge theory, for example, is a very good tool. And this relies on exactly this trick. But if you want to do dynamics, then you have to realize you're making life very, very difficult and in a sense, destroying the dynamics by doing this trick. Of course, the right-hand side here, you've now sort of lost, if all you do is work in Euclidean time, you lose the ability to define initial and final states and to study the dynamics. Your only way of doing that is by analytic continuation. And of course, that's a dangerous thing to do. If you make any kind of approximation at all, the analytic continuation may fail. So we do something else. We say, instead of rotating time, which is really a sort of dummy index in relativity, it's not a physical quantity, the time coordinate. So instead of rotating time, we deform the integration constant for the integral over paths. So that really is an integral dx, where dx is some kind of measure on the space of paths. We deform the contour over paths in order to make the integral convergent. Now, this path integral, when you think about it as an oscillatory integral, it's obviously the most oscillatory integral you could imagine. I mean, e to the I x squared is bad, but e to the I, standard model Lagrangian, integrated over all fields, that's extremely oscillatory. And for that reason, most people are just avoid it. But these two gentlemen, Picard and Lefschetz, gave a very interesting and general criterion for whether a given saddle point is relevant to an integral. So imagine in arbitrary finite dimension. So imagine you're doing some integral, let's say in one dimension along the real axis, and you want to rewrite this integral in terms of contributions from saddle points. And the saddle points may be on the real axis, or they may be in the complex plane. But in general, you want to know whether a given saddle point is relevant or not to the integral. It's very easy to construct examples where saddle points are relevant. For example, e to the I x squared, x equals 0 is a saddle point, which is definitely relevant because it's on the contour. But it's also very easy to construct examples where there are saddle points in the complex plane, often infinitely many, which are not relevant. Not relevant means that you cannot deform the original integral from the real axis onto the steepest descent contour corresponding to those saddles. So they're just in a topologically different class, and you cannot rewrite your original integral in terms of those. Picard's and Lefschetz's criterion is actually very intuitive. It says that to decide whether a given saddle point is relevant, what you do is go to that saddle point, and then instead of flowing downhill down the steepest descent contour, you flow uphill on the steepest ascent contour. If the steepest ascent contour intersects your original integration axis, or integration contour, then the saddle is relevant. It's if and only if. And intuitively, you can think of taking your original contour on the real axis and just sliding it down the steepest ascent contour from that saddle onto the saddle. There's kind of obviously a smooth path to take the intersection point down the steepest descent contour and onto the saddle. And so then it's relevant. And one of the things which led us onto this game was the claim of Hartle and Hawking that the Euclidean action for a force sphere in quantum gravity was e to the plus m Planck to the fourth over lambda. It's a very famous formula, which was the basis for all kinds of speculations about quantum gravity. But the one thing you can never get with Picard-Lefschetz's theory is an exponent which is positive, because I just told you why not. The theorem is that a saddle is relevant if and only if the steepest ascent contour, meaning that the real part of the exponent of the phase factor, the real part of the exponent, grows as you go from the saddle to the original integration axis. So you can never get exponents which are positive. And if you do, you made a mistake. And when I realized that all these famous people had made this terrible mistake, it made me realize this whole field has rather shaky foundations. So we've written many papers about the Hartle-Hawking instanton. It's just irrelevant to the path integral. And if you do the integral properly, you have to get a negative real part of the exponent. Now, our work has a slightly different spirit than Picard and Lefschetz's idea. Picard and Lefschetz, being mathematicians, sort of weren't necessarily that interested in the practicalities of things. And typically, you have an infinite number of saddles in any interesting problem, certainly in anything quantum mechanical. And so it's not very practical to really go to every single saddle and see whether it's relevant or not. But there's another much better way to proceed, which is you take your original contour and you just flow the contour downhill, and it will find all the relevant saddles for you. That's what it will do. And you just never even think about the others because they won't be found. So that's the spirit of our work. And we've written a couple of papers on it so far using that idea to solve all kinds of interference problems that were not possible to do before. What I'm going to talk about today is using this idea to define the Lorentzian path integral. And as I said, it should be useful in many contexts. And let me mention that most of this work is done with my former student, Job Feldbrugger, who will be coming to Edinburgh this September. So our definition implies the following exact formula. So people often think this is semi-classical, it's an approximation of some sort. It's not at all, it's actually exact. It allows you to define the path integral using the classical theory as an organizing principle. And so it really emphasizes the closeness of the classical and quantum formulations. So on the left-hand side, we have something fairly ill-defined, the usual path integral. And that's why I put equality here, because the left-hand side doesn't even really exist. The right-hand side is where our definition leads. It leads to this formula that the first thing you have to do is to find all the relevant classical solutions. And they may be real or they may be complex. And in simple examples, I'll show you they'll be infinite in number. In the simplest quantum mechanical theories, there are infinite number of classical solutions. That's all right. That's not too scary. It's a discrete infinity. You can write it down. Each one has a phase, a to the is over h bar. It's just a classical phase. But notice we're leaving all of them at once, and they're all going to interfere. Okay, so this is not just classical physics. This is the physics of phases. And then we have an integral. The integral here is over a real positive probability measure. And so we're going to use some concepts from measure theory here, which I must admit I'm a novice in, but I've been forced to learn. The mathematical theory of measures. And this measure exists on a space you can think of as a steepest descent contour. So every classical solution has a corresponding steepest descent contour. On the steepest descent contour, the real part of the phase, this is over h bar, the real part is monotonic. It starts at the classical solution where it gives you this value, and then its real part decreases towards minus infinity. So you're on a structure called a thimble. It's called the Lefschetz thimble. It's a monotonically decreasing positive function, which obviously gives you a well-defined probability measure.
Sorry, Neil, could I just ask, the classical solutions just real ones? Or they?
No, they could be anything. This formula is completely general.
So, so including like complex instantons?
If they're relevant.
Yeah, okay.
Yeah, you have to flow the theory. It will find the relevant ones. In the examples I'll do in detail, they'll all be real. But if we varied it a little bit, we would get some complex ones describing tunneling and so on. In the example I'll show in detail, there won't be any tunneling. So there's this positive, definite, real probability measure, but there's also phase. So it turns out that when you deform your contour, you've got to include the Jacobian from the original variables on the real axis to the variables running along this contour going into the complex plane. And that Jacobian has a magnitude and a phase, and this is its phase. You notice the phase doesn't depend on h bar because it just depends, it's all determined by the original action. So there is a phase here. In the limit, as h bar goes to 0, this measure factor becomes very sharply peaked. And in that limit, these phases become plus or minus pi over 4. And these are well known as Maslov indices. You get n pi over 4 in propagators, quantum propagators. And there's a very simple and geometrical explanation for all that in this picture. But notice it's pretty interesting that this phase has no h-bar dependence at all. It only arises as a consequence of integrating over this measure on the thimble. The J and C is the thimble for the classical solution labeled by NC. And on that thimble, the path integral is absolutely convergent. I should also tell you that it's a consequence of the Cauchy-Riemann equations that the flow equations, as you flow downhill on the thimble, the phase remains constant. That's why I could actually bring it out. So as far as the exponent is concerned, the phase part of the exponent is absolutely constant on the thimble. This phase only arises from the Jacobian in the change of variables from the original contour integral to the new one.
So just a question, Neil.
Yeah.
How does this relate to the Wheeler-DeWitt equation? I mean, can you actually find a bridge with the original canonical quantization, or is it?
Yes, you can. It is related at some level, though I think people are not fully aware that DeWitt completely disowned that equation. That equation is probably the worst defined equation anyone ever wrote down. It has ordering problems which are a total nightmare. And so to treat the Wheeler-DeWitt equation as fundamental is really building on quicksand. But nevertheless, there are some relations. I've just told you they come down to how you define the integration over your original contour, and also precisely what you use for this exponent. So there are issues, and I've put an NB here. There do remain ambiguities. They're related to choices of ordering in the Hamiltonian. And I think these problems just have not yet been resolved. Okay, so I'm going to be dealing with theories that are simple enough, basically non-relativistic quantum mechanics, in which those issues just don't arise. But they need to be dealt with, and maybe this approach will give us new ways of dealing with them. So yeah, it's early days.
But would you say that there is a mapping between, for example, measure uncertainties and ordering problems in the Wheeler-DeWitt equation specifically?
Yeah, they're related, that's for sure. But yeah, I don't really want to say more than that. There are, I mean, the most elementary ambiguity is what, of course, people are writing papers, a billion of papers on now, which is when you, for example, do the path integral for the Higgs boson, you can include a conformal coupling, psi r phi h squared, and people play all sorts of games with that. And non-gravitational physics just doesn't tell you what that coupling is. So a priori, you're free to do whatever you like. And so it's an extra parameter that you can play with in the standard model. And that's really very unsatisfactory because, yeah, there's no sort of principle governing what that factor should be. And this is also related to choices of ordering in the Hamiltonian. Okay, so let's do some oscillatory integrals.
Sorry, Neil, could I just ask a quick question before you go
Sure.
on? I was just wondering, so you normally have to renormalize or regulate the path integral before you can work with it. And
Yes.
if I thought of, for example, using a lattice regulator just even in space,
Yes.
and then thought about implementing something like this, how?
I will discuss this. I will discuss.
Okay,
this.
I was going to say the classical solutions you'll get are going to be strongly regulator dependent, I would have thought. Maybe, or...
No, so that's the whole point, is this construction is not dependent. In fact, the whole point of the proof we have is that it proves the limit exists. Okay, so I don't like lattices, they're really ugly. What we will do is use a natural basis to define the integration measure, and which is essentially like Fourier modes. It's sort of the Fourier modes appropriate to the theory. But your answers should not depend on that, on the specific basis. But yes, we'll come to that. I mean, the whole spirit of this is actually not to laticize the theory. It's to be guided by the continuum equations very, very closely. But we will be able to prove that the theory expressed in terms of these modes, as you take the limit that the number of modes goes to infinity, that there is a well-defined measure. Okay, so basically there's a generalization of so mathematicians will tell you that the Wiener measure, right, which is the most basic measure in measure theory, in infinite dimensional measure theory, the Wiener measure exists, I mean, independent of any regularization. And so the measures we're discussing are the analog of that. That's like a Brownian walk where you describe quantities which are actually independent of all the details of the step size and so on. And the Wiener measure for a Brownian walk is independent of cutoff.
Thanks.
Okay, so let's do some oscillatory integrals. And the obvious one to start with is the Gaussian, e to the ix squared. And a physicist's way of tackling this might be to put a cutoff, r, and negative and positive, and then take the limit as r goes to infinity, and this works very nicely. The integral just converges. You can plug this into Mathematica and plot the answer, and you get the what's called the Euler spiral, and it has a definite answer. However, this is only conditionally convergent. It's obviously not absolutely convergent, because if I took the absolute value of the integrand, that would be 1. And the integral would just be 2r, which tends to infinity. So it's not absolutely convergent. It means that the order in which you add things up is crucial. This turns out to be hopeless as a way to proceed. Sorry, I said that too soon. I want to introduce the other way of doing the Gaussian, which is steepest descent. So you say my original contour from minus r to plus r, I deform it into the complex plane, so it has a 45-degree line on which e to the ix squared is just e to the minus s squared, so a nice monotonic Gaussian. And then it has these two arcs at infinity. With a little bit of algebra, you can easily prove that in the limit of large R, the arcs at infinity tend to 0. And so the original integral is exactly equivalent to this integral over the Lefschetz thimble in the limit as R goes to infinity. So that's a much nicer way to do the integral. And imagine you were doing this numerically. You would start off with the blue function, which oscillates with amplitude 1 off to infinity, and you will struggle to make your integration code converge. But if you do it on the yellow contour, it's a Gaussian and converges extremely quickly. And in fact, this was another reason we came to this. It turned out that radio astronomers were doing interference patterns by integrating along the real axis. And so putting all their integrals on massive supercomputers and trying to get all these phases to cancel. And that's really a terrible idea. because then, you know, it all ends up depending on the cutoff. Now, this method of using a cutoff is hopeless in higher dimensions, as I will explain, using a sharp cutoff. Let's go to 2 dimensions. So imagine I've got this 2-dimensional integral, just the product of these 1-dimensional integrals. And if I literally take the product, then what I'm actually doing is a square cutoff in the space of x and y. And then, of course, the answer is just the square of what I had before. But why choose a square cutoff? Why not choose a round cutoff? If I choose the round cutoff in 2D, I'd go to polar coordinates and do the angular integral. And then I'd be left with this integral, r dI dr squared. Now, this is a lot worse because the r factor here in the measure is growing. So not only is this oscillating, but the amplitude of the oscillations is growing with r. Now, this is you can do this integral exactly. That's the answer. And try taking the limit r goes to infinity. Well, there's no limit because it just goes like e to the ir squared off to infinity. So what this is telling you is that in higher dimensions, your answer will be to depend on the shape of the cutoff. And for some shapes, it just won't exist. So do we give up? Well, before we do, let's go to even higher dimensions. We've got to do infinite dimensions with the path integral. Consider this integral where I'm now in d dimensions. And you can quickly see that when I do the integral with the sharp cutoff, I get this huge growing term. You know, basically the last oscillation will dominate the integral. But then if you do an asymptotic expansion, you discover that at subleading order, there's a very beautiful answer, but it's sitting under this awful term, which you really don't want. What's the answer? The answer is to say that the way interference works, and should work, is you never want to use a sharp cutoff. What you want to do is to allow the phases to cancel. You want to allow destructive interference. And so what you do is define the, so for example, if a particle is traveling from me to you, and it can go via the moon, I don't want to cut, I want to allow all the paths going via the moon to cancel each other. So I don't want a cutoff at the moon. I want a smooth cutoff. I don't want a sharp cutoff at the moon. I want a smooth cutoff, which will allow all those paths to cancel. So this is what we do. We introduce a smooth cutoff, just Gaussian in this case, with some radius r. And then, of course, the integral, then all the cancellations happen. We get the nice answer at leading order in r, and then we get subleading terms which go to 0 as r goes to infinity. So this is how to do oscillatory integrals. This is the first step.
Sorry, can I ask you a question?
Yeah.
So if instead of explicitly calculating the partition function, you calculated a generating function or putting some source term in there, and then looked at not the partition function, but 1-point functions or 2-point functions, are they ever not cutoff scheme dependent? Because I think that's a more physical observable than just the partition function. That's a number, right?
Yeah, just be careful. Don't use the language of partition functions because I'm precisely not doing statistical physics. Okay.
Well, I could still imagine putting some, you know, JX in that.
No, we will get to that. This is called, the theorem we will rely on is called the Bochner-Minlos theorem.
Hmm.
And it says precisely that when trying to prove whether a measure exists, what you actually do is calculate the characteristic function of the measure. For infinite dimensional measures, the characteristic function is much easier to deal with than the measure itself. So exactly what you do is insert e to the I jx, say for quantum mechanics, integrated over t. You introduce a source, and then you end up proving that that expectation value exists.
Okay.
And has various properties. It has to have positivity, it has to have continuity. And if it satisfies all that, then there's a rigorous theorem that says there is a good measure.
Thank you.
So we're exactly going to use sources. And once you have these sources, you can now calculate any correlation function you're interested in, of course. and also other quantities like expectations of phases, e to the I kx, and other variables. So yes, we will introduce sources. Generally, the sources don't affect the convergence of the integral much at all, because they're linear in x, and all the theories we're going to deal with are nonlinear, and so the convergence is determined by the terms in the Lagrangian, not by the source. Okay, so we want to introduce a smooth cutoff, but cutoffs are ugly. We'd like our answers to be independent of cutoff. And then there's a very beautiful result, which is that the result for a smooth cutoff, and there's an infinite class of such cutoffs, where you take the cutoff to infinity at the end of the calculation, you can get that result without using a cutoff at all. And the way you get it is by using Cauchy's theorem and deforming the integration contour onto the steepest descent contour, and then showing that the arcs at infinity vanish in the limit as the cutoff goes to infinity. So now let's just do an example, because it's very cute the way this works. So let's do this horrible integral, r to the d minus 1 e to the I r squared, and imagine d, capital D, is very large. So try and do this numerically, and yeah, you would fail immediately. But instead, I insert my smooth cutoff. And then what I do is deform the contour to the steepest descent contour plus the arc at infinity, or at large radius. And Cauchy's theorem guarantees the two integrals are identical. So yeah, I haven't described this quite right. Theta is actually the angle on the contour. This angle is pi over 4. I'm sorry, that's just a typo. This angle is pi over 4. Theta is the angle on the contour. So let's look at this arc at infinity. Here is the dr. It's just I d theta, L e to the I theta. That's the dr. I've got to go from theta being pi over 4 to 0. And then I integrate this function. This function is just the integrand, but with r complex now. Now, in a few lines, it's easy to show that the modulus of that integral is bounded by the following expression. That should be a capital D. I'm sorry, not a small d. So if I took r to infinity, the bound would be L to the power D. Right, which would be terrible as L gets large, because it just gets bigger and bigger. However, for any finite value of r, as I take L to infinity, this goes away, right? And then I take r to infinity at the end. So the limits r going to infinity, L going to infinity do not commute. And what you have to do is define the theory for some finite r, some smoothing scale, like the distance to the moon or whatever, or bigger, and leave that scale there, deform your contour, push the arc at infinity to infinity, where it will disappear, and then you end up doing the calculation on the steepest descent contour. And at the end, you can take r to infinity. So nothing depends on the cutoff radius r. But you have to be aware there's this subtle order of limits issue. And so I would argue physically this is the correct thing to do. So let's do an example, the quartic oscillator. So this is the simplest quantum system that's not Gaussian. We're going to see there are all kinds of features here which make it a very interesting sort of laboratory for path integrals. So emphasize, it's not gravity, but it's not too far away from Higgs model or Yang-Mills theory or whatever, because it's x to the 4th. Can we do the path integral? Sorry, was that a question? Okay, so I write it in this way. Namely, sort of motivated by relativistic thinking, that we use the parameter time t, which always goes from 0 to 1, and then the physical time, capital T, is the distance, is the time, initial and final time, difference between the initial and final times. It's nice to write it this way because various things become easier to understand. In particular, you'll notice that if you write the Hamilton-Jacobi equation, that the differential of the action with respect to the total time, it's very obvious that it's just the energy or minus the energy in this formulation. So here are the classical equations of motion, and my boundary conditions I'm going to use. And again, just for simplicity, let's take boundary conditions where the particle starts at 0, x equals 0, and ends at x equals 0. We can generalize this, but it becomes a little bit more messy. Now, the first thing you realize is that for the quartic oscillator, with those boundary conditions, there's a countable infinity of classical solutions, right? So this is qualitatively different than the harmonic oscillator. Harmonic oscillator, the equations of motion are linear, and linear equations always only have one solution. So, but these are nonlinear equations, and they have infinitely many solutions. And physically, what happens is that I could throw the ball to the right, and it bounces once and comes back, or I could throw it to the left. So there's actually twice this number of solutions. Or I could throw it a bit faster, and it would come back in the same time, but it would have bounced twice. Or I could throw it even faster, or faster and faster and faster. So there's a kind of quantized set of classical solutions which increase in energy, and they all satisfy the boundary conditions. In this particular case, these solutions are very nice. This is a scale invariant theory, the x to the fourth. And the solutions are Jacobi elliptic functions, which are basically nonlinear versions of the sine trig functions. And so here they are. The lowest solution doesn't go that far and just bounces once and comes back. The next solution goes a bit further and bounces twice before coming back. Here's the next solution. And roughly speaking, these are sine waves, but they do have some nonlinear aspect. Here is the energy. It goes like this classical quantum number to the fourth power, and the action similarly. And the action goes like 1 over the time cubed, and that'll be important in a moment. Now, let's think about doing the path integral for this problem. The fact that the classical solutions basically look like Fourier modes, some slightly nonlinear version of a Fourier mode, suggests that working in the Fourier basis might be, or at least roughly, a good picture. And so let's think about the complex plane for every mode coefficient. So I think about the path integral measure as being integral dxn, where xn is the nth Fourier mode coefficient. Actually, we won't quite use Fourier modes, but they are good enough to think about. Integral dxn, and then product over all n in principle. And here Toby's remark comes in. What we will actually do is take a finite number of mode coefficients, define everything, prove properties about the finite dimensional integral, and at the end of the day, take the limit as the cutoff on the mode number goes to infinity. Now, we're going to define an h function, and I think I forgot to do that. Let me see, maybe on a later slide. Yeah, so h is what I call a height function. So is is the action, and then h is just the real part of is. And so the magnitude of the integrand is determined by the real part of the exponent. Okay, so that's what h is. So the h is a height function, and it has the following saddles and steepest descent contours. So what I've plotted here is a picture of a complex plane for one of these mode coefficients. And just to get a feeling for what it looks like, imagine you just draw this, take the function to be x squared. This is representing the kinetic term contribution. X to the fourth is the potential contribution, and just draw the corresponding height function. So obviously x squared minus x to the fourth has three saddles, three real saddles, one at x equals 0, and then one at positive x and one at negative x. And then each saddle gives a steepest descent contour. And the way you find those contours is by flowing downhill in the height function h. So you follow what's called a gradient flow downhill. Near the origin, you're going at 45 degrees, because that's just basically determined by the x squared. So it's just like the Gaussian integral. But as you go off to larger x, the x to the fourth becomes more important. And it turns out the steepest descent phase is 3 pi over 8 for x to the fourth, and then minus pi over 8 is the other end of the thimble. So, but notice what's happened. We took the original contour and we just pushed it into the complex plane, again, relying on Cauchy's theorem to ensure the integral is unchanged. And we ended up with 3 thimbles, one per saddle point. Now, let's think about the Wick. So this is what we have to do. This is the picture we have of how we do the path integral. Every Fourier mode is going to be deformed into its complex plane. And what we're going to prove is that the integral so defined, okay, where every Fourier mode got integrated over these 3 thimbles, which are very steeply convergent, that the resulting integral is well defined. Let me just talk briefly about the Wick rotation. What would the Wick rotation have done to this theory? And I'm going to explain the Wick rotation is really disastrous in the following sense. You take the Lorentzian theory and you rotate the time. Okay, that's the idea of Wick rotation, is I rotate the final time down to the negative imaginary axis. So t, capital T, goes to e to the minus I theta t, where theta goes from 0 to pi over 2. Now, in all the formulae I've written down, the classical solutions still satisfy the boundary conditions. That's because I use this parameter time t going from little t going from 0 to 1. So these are still good solutions to the Wick rotated theory. However, if you work out the action, I told you it goes like 1 over t cubed. And so now all you have to do is substitute t goes like e to the minus I theta t into this formula. So this now goes like e to the 3I theta, multiply by I and take the real part, you get minus sine 3 theta. So I started at t equals 0, started to do my Wick rotation. The exponent, is classical, became negative. That's good. It means it can be relevant to the integral. So the classical saddles I showed you are still relevant. But now what you notice what happens is when I get to pi over 3, the real part of the exponent becomes bigger than 0. That means they're irrelevant. So these classical saddles, which were relevant, they were on the axis, when I did the Wick rotation, they became irrelevant. So Wick rotation so the Wick rotated theory does not have these classical solutions as saddles at all. And obviously, you've thrown out a major part of the theory. You've thrown out an infinite number of classical solutions in going to this Wick rotation. It's a very dangerous thing to do. Formally, there's nothing wrong with the Wick rotation. It's absolutely fine. You just write things in terms of energy eigenstates and, you know, e to the minus I e t, you can rotate t. That's fine. The problem is the sum over the classical solutions, the path integral will only become a sum over classical solutions if the saddles are relevant. If they're not relevant, it's not going to be representable that way. So conversely, if you want to recover the classical solutions by analytic continuation from imaginary time, it's going to be exponentially difficult because they are non-perturbative contributions to the real-time theory. And if you did any approximation in the Euclidean version, you simply wouldn't see, or you wouldn't represent these classical solutions properly. So, okay, so let me just stop and see if there are any questions at this point.
Before we ask questions, Neil, can I ask how much more there's going to come? Just because we are nearing the hour mark.
Ah, right. Okay, let me just see. Let's see, about 10 minutes.
Yeah, sure.
Is that okay? People are welcome to leave. I won't even see you if you do. Okay, so let's try. I just want to say some words about a rigorous construction of the path integral in this way. Again, it relates to Toby's question. You want to express the theory in terms of a natural basis of modes. And in particular, in view of this in view of this construction of the thimbles, it makes sense to work in terms of how the theory behaves near a saddle, okay, because that's kind of where it's easiest. So let's expand the fluctuations. So we take a classical solution. Each classical solution defines a thimble. And then let's expand the fluctuations about that thimble, right, in terms of the eigenfunctions of the quadratic operator at the saddle. That's the natural, this is the Gaussian approximation to the action near the saddle. So the operator is typically some kind of Schrodinger operator. It has an infinite set of eigenfunctions, and it makes perfect a complete set of eigenfunctions. It makes sense to expand the fluctuations in that basis. So now we're going to define the propagator as follows. This is a bit technical, so let me not worry about this. Essentially, you multiply and divide by the free particle propagator. It just technically makes things easier. We take our integral over these mode coefficients. We deform it into the complex plane. We have a trivial thimble for every mode. That's the J0, where everybody goes on that thimble. And we have the non-trivial thimbles where one mode goes on this thimble and everyone else goes on the J0 thimble. And then there are infinite sum of such terms. Now, what we need to show is that this H function converges rapidly enough as we go downhill in order that this path integral really exists. And by exists, what I mean is I can take the limit as the cutoff in mode number goes to infinity and everything is well defined. So you can study these flow equations. They're a little bit scary at first because they are PDEs, even for ordinary quantum mechanics. You've got T, your parameter time along the path, but you also have tau. Tau is the flow parameter. You're flowing downhill in this height function H. And so you have to solve these PDEs in order to discover this thimble, the Lefschetz thimble, which is a half-dimensional subspace of the complexified space of paths. But they're not so bad. Well, you think about these equations carefully, actually you can solve them analytically at small x as a power series expansion, and that's almost good enough because you just go to a few terms and you find your height function h is so negative that you're not going to get any other contributions from the rest of the contour. You can also analyze them at large x to prove that the integrals really converge. And here's some pictures of the paths. So if I take the simplest path and I flow it downhill, essentially you flow up this curve here in a very well-defined way. Now, one can show that rigorously from the flow equation, that the height function decreases faster than quadratically at large x. It's not surprising. It's got some quartic terms. And this is enough to show that there exists a bounding Gaussian theory, that I can take my whole thimble in this space of arbitrary number of coordinates and just enclose it with a Gaussian. And the Gaussian, furthermore, is a free theory, a theory of free quantum mechanics. And for that free theory, there's the Wiener measure, which has a good limit. And actually, this is enough to prove that the measure exists in the full interacting theory. So there's some technical terms here. We have to use something called Lebesgue's dominated convergence theorem to show that essentially that this characteristic function is continuous, which is one of the criteria for a good measure. This is Bochner-Milnos theorem. You have to essentially prove positivity. You've got to show that this d mu, and you can show directly from the characteristic function that the measure d mu is positive due to this Bochner-Milnos theorem. And then, as I said, the phase factor arises from the Jacobian between your original integration variables on the real axis to these variables on the thimble. It arises from the contour deformation. Now, interesting point is that the sum over classical solutions does not converge in this theory. And in generic non-relativistic quantum mechanics theories, anything with a potential which confines you will have the same property. Infinite number of classical solutions, and the sum of them does not converge. Doesn't mean this is a disaster at all. It just means that the Feynman path integral propagator is in general only a distribution. And it's a funny thing, but this doesn't seem to be recognized in books on quantum mechanics. They behave as if this propagator exists as a function. It does not. It only exists if you smooth it, if you integrate it. So for example, if I take the time smoothed propagator, here it is, take the Feynman propagator and then smooth it over the initial time. Here I chose an exponential. And now I look at it as a function of t, the final time. We get the usual 1 over root t. This is what the free particle behavior, which is universal. And then you get this jagged function. But as you raise the cutoff, this is actually 2 curves on top of each other with different choices of smoothing. Different choices of the same smoothing, different choices of cutoff in n. And as you send the classical cutoff n to infinity, it does converge, but the answer depends on this smoothing scale. So this is all due to interference. Here's a picture in real space. This is the Feynman propagator for x to the 4th theory. You see the classical solutions in here. They're interfering like crazy. They're creating caustics in the interference pattern. And but again, even this picture is also dependent on smoothing. Very fascinating thing is that in relativistic theory, there's a weaker dependence and perhaps no dependence at all on the smoothing. Relativistic theories seem to be better behaved than non-relativistic quantum mechanics. So it's not too surprising because they have a limit on the speed of light, or speed of signals. So there's a very close interplay between quantum and classical pictures. Constructive interference between the quantum modes leads to a discrete set of classical solutions. Likewise, the interference between the classical solutions yields a semi-classical quantization condition. And I won't have time to describe it, but this is all made much clearer by this construction. And the factor of a quarter here is essentially that phase I was telling you about. So I want to just also show one, this is a pointer to how space-time should emerge from the path integral. When we do quantum mechanics, we're usually told never to look inside a quantum amplitude. And S-matrix theorists would be the first to say this. that the only meaningful thing is the S matrix. And so I take the opposite point of view. There is no S matrix in nature. All processes of relevance to experiment are virtual, not real. Nobody has ever seen a real particle in nature. Everything is virtual. Just because experiments are conducted in finite volumes and finite times. And so there's no such thing as an on-shell particle. And it's particularly dramatic in cosmology, where the universe has only lasted a finite time. So what on earth are you doing thinking about the S matrix? It's not something you could ever measure. That's, of course, slightly rhetorical, but not too rhetorical. Now, what do you do if you can't talk about the S matrix? Well, you talk about something called the weak density. And these are ideas pioneered by people in quantum foundations, Yakir Aharonov in particular, of the Aharonov-Bohm phase, which is that you deliberately look inside quantum transition amplitudes. And essentially you couple your measuring device to the quantum system weakly. It's like us observing the universe. I mean, we don't change the universe. It's much bigger than us. We are weak observers in the universe. And you study the dynamics of the system and make predictions for what anybody who observed it would see. So this is the weak density in x to the 4th quantum mechanics. And what you can see, unfortunately, this does depend on smoothing because it's non-relativistic. But what you can see here is the quantum mechanical propagator, and you form this quantity. This quantity allows you to compute expectation values of anything which a weak measurement would measure. Okay, so literally it's sort of the best characterization of the system for weak measurements. And here you see the classical solution emerging in a completely quantum quantity without any strong measurement. And this, I believe, is exactly how Wheeler envisaged space-time emerging in quantum geometric dynamics from interference. Throwaway comment, for pre-relativistic particles, this all works perfectly. Relativistic path integral gives exactly the Feynman propagator. There's no need for I epsilon, Wick rotation, anything else arbitrary. This is exactly how you get the propagator in relativistic quantum mechanics. So I just want to end by showing you some pictures. I mentioned at the beginning, path integrals are being done everywhere in the universe on enormous scales. And in gravitational microlensing, one, for example, looks at the bulge in the galaxy where there are lots of stars and many binaries or planetary systems around those stars. So something like 2,000 planets have been already discovered through their impact on, through their lensing effect. It's called microlensing. As the planet moves past the line of sight, it creates a caustic because it bends the light and causes an overlap in light rays. So you get spikes in the intensity, and you can use those spikes to detect planets or stars in the galaxy. So that's a very well-established technology. If you try to do this in wave optics rather than geometric optics, the only problem which was solved in wave optics was a point mass, a single point mass. And that was solved, I think, in the 80s. But nobody could do binary lensing or anything more complicated using wave optics. And the reason was that this interference integral, which they call the Fresnel-Kirchhoff integral, it's just the path integral. This integral is oscillatory, and they couldn't calculate it. So yeah, I'm not going to say about the physical realism unless somebody asks, but in a nutshell, yes, this will be observable in 10 or 20 years or so. And these are the patterns. So here's a binary gravitational microlens. This is the pattern of caustics. So as you see a background star cross this picture on a line, you would see two spikes in the intensity. and these are now routinely detected. And so one of these might be a star, and one of these a Jupiter. So this is routinely seen now. But what was not possible was to compute the wave optics pattern. And so this is what we did recently. Here it is. The beautiful thing is that the wave optics pattern, the spacing of these diffraction fringes, directly tells you the masses of the point, actually the mass scale of the point of the lenses, which is not possible to get from this picture because there's a degeneracy between the masses and the distance. So in the wave optics, because of the wavelength of the radiation, you essentially have a local measure of the mass, the lensing mass. And so if we're able to see these patterns, we will directly be able to infer the mass of the lenses. And this is a calculation with lenses at multiple redshift, which is just way beyond what other techniques could do. Thank you.
Yeah, let's thank Neil for the very nice talk. And I'm sure there are some more questions.
I have a question.
Sure, Kelly, go ahead.
Yeah, Neil, so you began your talk by saying that Hartle and Hawking got it wrong with the no boundary proposal.
Yeah.
Now, Alice Tucci and Jean-Luc Lehners wrote a paper in which they showed that the no boundary proposal could be recast in terms of this this kind of technology that you're talking about, but with Rho-bound boundary conditions. So I wonder if you could translate your indictment of Hartle and Hawking into that language.
Yes, I mean, the price of rescuing Hartle and Hawking was to introduce a boundary. And unfortunately, that means it's not no boundary. So the price of the rescue was, I think, worse than the problem. I mean, we can all introduce a boundary to the universe. That's how we do the theory of cosmology. We just start the universe at some point. The whole attractiveness of Hartle and Hawking's no boundary proposal is that it seemingly did not require a boundary, an initial boundary. So if you replace it with some other boundary, then from my point of view, it just loses its attractiveness completely.
Does this have an interpretation in terms of what you were describing as relevant and irrelevant symbols?
No, I think the way Lehners and Tucci have done it is they, well, as their work says, they simply introduce a boundary and then tweak it in order to make the path integral more sensible. Our work shown that if you sort of honestly implemented no boundary, quote, boundary conditions, in other words, just summed over initial manifolds without boundary, then you got a completely disastrous path integral. It didn't mean anything, where the fluctuations were completely out of control. So they showed that if you do introduce a boundary, you can put the fluctuations back under control. That's not really very surprising because you're essentially putting in by hand that the fluctuations are small. So I don't regard that as a real solution. It's no better than people who do inflation who say, well, I'm just going to assume, you know, an inflating initial universe.
I don't think they viewed it as a salvation of Hartle-Hawking. I think they viewed it as a translation.
Yeah. Possibly. I mean, I know Jim Hartle and Thomas Hertog are still, and I think Jonathan Halliwell are still valiantly trying to get around this problem. And you know, I wish them all the best of luck with doing that. But unfortunately, this very, you know, elementary argument that if you define the path integral starting from the Lorentzian theory, and I think it's very hard to argue with that, then you know, and then and if you use the instantons, which are complex solutions of the Lorentzian theory, but if you only take the relevant instantons, then it does not give Hartle and Hawking.
Okay, thanks.
Then there's a question by Faye. Faye, can you unmute yourself?
Yep. Hi, Neil. Thank you
Hi,
for
Faye.
a stimulating talk.
Thank you.
So in the gravitational path integral, sort of conceived of in the continuum, there's a choice to be made about whether you sum over manifolds as well as metrics.
Yes.
I think you briefly alluded to the sum over topologies.
Yes.
So Bryce DeWitt didn't like the sum over topologies, and he wanted to restrict the gravitational path integral to a single manifold, presumably some product manifold of some, spatial 3 manifold, presumably, and across time. And the reason that he gave for wanting to do that is that he couldn't see a way, because if you have these sort of topologically distinct sectors in your path integral, then he didn't see that there was a way to fix the relative phases between these different components of the gravitational path integral. Anyway, he wanted to restrict the topology just to one manifold. But most other people, I think, will probably want to include the sum over topologies in the path integral. And in particular, at the moment, there are many people are very interested in wormholes and path integrals for quantum gravity, which include, and you can't have wormholes unless you're going to consider a sum over topologies as well. So the question is, to what extent I know you haven't got onto gravity yet, but when you do, do you imagine that, to what extent do your ideas, do they demand that you are really considering contours? The idea that you're integrating along a contour, and that there's some space of histories that you're, that makes sense as being distributed, and that you can, that the concept of contour makes sense. If you're going to consider sums over topologies as well, it seems like that's a very difficult thing to maintain. So what is your perspective on that? On whether you're going to include sums over topologies, and if you are, then how does this concept of contour survive? Right.
So yeah, great question. And so I think at a primitive level, what I would like to do is cosmology in perturbation theory around a class of simple spacetimes. I mean, that's the least ambitious thing you could do. Just take FRW universes, maybe a torus or a sphere or something, and include all the gravitational perturbations and do this Picard-Lefschetz theory. And so we sort of half have done that. All the indications are it makes perfect sense. You can frame any sort of reasonable transition amplitude in that way. So that's a sort of minimal thing to do, but you're asking about much more ambitious things. All I can say is that, and it's way beyond where we've gone. So all I can say is the following, is that even the notion of complexifying the geometry is not without problem, okay? So it's easy enough to think about a particle's path in space-time, x of t being now x of t plus iy of t, or z of t being x of t plus, you can imagine complexifying a path, but a 4-manifold is a considerably more involved thing. Now, there's this is not going to answer your question, but there's some very interesting recent mathematical work by Kontsevich and Siegel, and they were asking, if we generalize the notion of, in their case, a Euclidean metric to a complex Euclidean metric, how far can we go? You know, so if you did this as a physicist, you might say, well, allow anything, and the signature, let's say the eigenvalues of the complexified metric could be anything. And they say no. They say they put very, very tight constraints on what you're allowed to do. It turns out that their construction or their arguments do allow you to go from Euclidean to Lorentzian, okay? But that's about it. You can only change one of the space coordinates into a time. And so I don't understand their work well enough, but I think it's great. They're beginning to think about complex geometry. What is the set of complex geometries? And I suspect there are going to be lots and lots of constraints beyond the sort of naive notion of just making G mu nu any complex function of the coordinates. So it's not a very good answer, but I think we have a long way to go. And I actually hope that string theory may give some insight, because in string theory, you do this. Of course, the way string theory is almost always done is strictly perturbative. So, these questions may be hard to answer even in string theory, but it really is the ideal place to use as sort of laboratory for path integrals and the idea of complex geometries. In string theory, as you know, Bryce DeWitt pointed out this contradiction, that if I said the string was actually embedded in Minkowski space, then I would find the geometry of the trouser diagram was singular. And so in string theory, they have in practice found ways to get around this, which I suspect are actually just using Picard-Lefschetz theory, but it is not, even that hasn't been described that way.
Thank you.
All right, then we have a question by Jonathan.
Hi, Neil, thank you for this talk. Tom Hertog, Jim Hartley and I are indeed valiantly continuing our work. There are still questions here that I've never seen properly answered. So you're very down on the Wheeler-DeWitt equation, causing it horrendously ill-defined. In practice, every application of it, pretty much, has been in the context of many superspace models or many superspace plus perturbations. So you're only just looking at a few modes. So the Wheeler-DeWitt equation, it's then just quantum mechanics, finite dimensionally, and likewise the path integral and the very clear relations between them. But what this raises, though, is the general question. I mean, you're not terribly clear in some of the calculations here and elsewhere what sort of object you're calculating. Is it a wave function, an amplitude, a green function, or whatever? I mean, that's an important thing to establish.
I feel it is clear. I'm calculating the propagator. That's it.
Okay, fine, it's a propagator. But then there is in all quantum mechanical situations, there's an equivalent canonical formalism in terms of states and operators and so on. But do you disregard that? Just say
no, I don't disregard that. And it's often very useful. What picture I have in mind is to reconcile geometry with quantum mechanics. The appeal of the path integral formalism is that it's geometrical. You sum over paths. The operator formalism, nothing is geometrical. It's all just a bunch of algebra. And to me, it seems that if you really want to understand what quantum geometry means, the path integral is the optimal tool, but then you have to make sense of the path integral. So that's my motivation.
I think we'd all agree with that there's a path integral, naturally, you can see the geometric side, but then when you look more closely at the connection between that and more canonical things, you can actually quantum mechanically have strings of projection operators that project onto sequences of three geometries, and it's there. I mean, they're not different things. They are actually closely related. So I always get uncomfortable if someone's claiming there's a path integral thing, but there isn't an equivalent canonical formulation.
I don't think I did claim that.
Not specifically here.
Mathematical
you did say the Wheeler-DeWitt equation is horrendously ill-defined. Would you?
Well, okay, yes. So you're right. You're right. You're right. I should have also said the path integral is equally ill-defined, which I think is fair. They're both currently, the path integral for gravity, I would say, is not defined at all. And I think, you know, when people, for example, people doing holography sort of claim that they have a duality between some boundary theory and some bulk theory, which is supposed to be gravity, and they usually treat it as Euclidean path integral. You know, this is really meaningless, unfortunately. So no, I'm equally damning about other things. It's not particularly it's not just that. I mean, I think the whole field is really in a strange state. And for me, it's actually very exciting to discover that the path integral, you know, this was news to me, that I mean, I've obviously heard people say, you know, path integral is always a bit dubious. My advisor, in fact, David Olive at Imperial, used to always say, oh, path integrals, don't use those. You know, the operator formalism is the only meaningful formulation of string theory, for example. So that's a widely held view. But it didn't really come home to me how fundamental the problem is until I started working on it. And then you just realize that in a certain sense, nobody knows what they're doing. And when they start doing non-perturbative things like using saddle points, and then they have no idea which saddles are relevant or irrelevant, you know, you realize the field is really without foundation. So what I'm trying to do is to help build some foundations.
Well, I agree with some of those issues, but then...
sorry, Jonathan?
Yep.
Maybe it's a good point to end the official part of the seminar.
Okay.
But feel free to stick around and we can have some further discussion. So let's all thank Neil again. And as I said, yeah, please feel free to stay.